Welcome to this coding walkthrough. Today, we'll dive into problem number 1278, Palindrome Partitioning 3. This is a fascinating problem that combines dynamic programming with string manipulation to achieve optimal solutions. Let's get started. In this problem, we are tasked with partitioning a string S into k non-empty substrings. The goal is to minimize the total number of character changes required to make each substring a palindrome. A palindrome is a sequence that reads the same forward and backward, so for each partitioned substring, we calculate the minimum changes needed to achieve this property. The output is the minimized sum of these changes. The input consists of a string S of length n, where n can range from 1 to 100, and an integer k such that 1 equals k equals n. The output is a single integer, which represents the minimum number of character changes required to partition the string into k palindromic substrings. For example, if the input string is S equals ABC and K equals 2, the output is 1. Here's why: we can partition the string into two substrings, such as A, B, C. The first substring, A, is already a palindrome, so no changes are needed. However, the second substring, BC, needs one character change to become a palindrome. We could change B to C, or C to B, resulting in the palindromic substring CC or BB. The total number of changes required is 1. This demonstrates how the problem focuses on minimizing the total changes across all partitions. Now consider another example where S equals AP and K equals 3. The output is 0. In this case, we can partition the string into three palindromic substrings, AA, BB, C. Each of these substrings is already a palindrome, so no character changes are necessary. The total number of changes required is therefore 0. Another example is S equals LeetCode with K equals 8. Here, each character of the string forms its own substring, such as L, E, E, T, C, O, D, E. Since single-character substrings are always palindromes, no changes are needed, and the total number of changes is again 0. The constraints of the problem ensure that k is between 1 and the length of the string, and the string consists only of lowercase English letters. Additionally, the result is guaranteed to fit within a 32-bit signed integer. For edge cases, if k equals the length of the string, the output is always 0 because each character becomes its own substring. If k equals 1, the output corresponds to the minimum changes needed to make the entire string a single palindrome. Lastly, if the string is already a palindrome, the output is 0 regardless of k, as no changes are needed. These edge cases help clarify the boundaries of the problem and guide us toward an efficient solution. When tackling this problem, one initial approach we can consider is the brute force method. Here, the idea is to generate all possible ways to partition the string S into k substrings and compute the cost of converting each substring into a palindrome. To transform a substring into a palindrome, we would make changes to mismatched characters at symmetric positions. While this approach ensures that we eventually find the minimum cost, the sheer number of possible partitions makes it computationally expensive. Specifically, enumerating all partitions leads to an exponential search space, with a time complexity of O(2 to the power of n). For each partition, the cost of making substrings palindromic adds an additional O(n) complexity, giving an overall time complexity of O(n*2 to the power of n). This becomes infeasible for larger strings, such as when n is 100. To address this, we turn to a more efficient method, dynamic programming. In this optimized approach, we break the problem into smaller subproblems. First, we define dp, I, j, as the minimum cost to split the first I characters of S into j palindromic substrings. Additionally, we pre-compute cost, L, R, which represents the minimum number of changes required to make the substring S, L, R plus 1, a palindrome. By leveraging these definitions, we can structure the problem in a way that avoids the exhaustive enumeration of all partitions. Next, to solve the problem using dynamic programming, we compute the values of dp, I, j, iteratively. For each I, j pair, we consider all possible positions p where the last partition could start. Using the transition formula, dp, I, j, is updated as the minimum value of dp, p1, j1, plus cost, p, I, over all valid p-values. This means we are evaluating the cost of adding the last palindromic partition to the previous j1 partitions. The final answer to the problem will be stored in dp n k, representing the minimum cost of splitting the entire string into k palindromic substrings. To achieve this, the algorithm precomputes cost, L, R, for all substrings using a two-pointer approach, which simplifies the process of checking palindrome properties. The time complexity for precomputing the cost values is O, n squared, and filling the dp table requires O, n squared asterisk k, leading to an overall complexity of O, n squared asterisk k. This is a significant improvement over the brute force approach. In terms of space complexity, the dp table requires O, n asterisk k, which is manageable. While there is an alternative greedy approach that focuses on minimizing the cost locally at each step, it cannot guarantee a globally optimal solution because of the dependencies between partitions. The dynamic programming approach stands out as the chosen strategy for this problem due to its balance of efficiency and correctness. By precomputing the values of cost, L, R, and iteratively optimizing the dp, I, j states, this method ensures that the solution is both scalable and accurate for larger inputs. The brute force method, while guaranteeing correctness, is computationally prohibitive due to its exponential time complexity. On the other hand, the greedy approach is faster but sacrifices the guarantee of finding the optimal solution. Dynamic programming achieves the best of both worlds. It explores all possibilities to ensure correctness while significantly reducing the computational burden compared to brute force. Moreover, this strategy is flexible and can handle edge cases effectively, making it well-suited for the problem of partitioning a string into k palindromic substrings. In summary, the dp approach offers the best trade-off among time complexity, space usage, and solution accuracy, making it the most practical choice for solving this problem efficiently. To solve this problem, we need to partition a string S into k substrings such that the total cost of converting each substring into a palindrome is minimized. A change here refers to replacing a character with another to make the substring symmetric. The first step is to understand that we must divide the string into exactly k parts, and each part must be transformed into a palindrome at the lowest cost. Now, considering the various ways to split a string of length n into k parts, we realize that evaluating all these partitions requires an efficient approach. One of the key observations is that we can precompute the cost of converting any substring into a palindrome in advance, which significantly reduces redundant calculations. To handle this systematically, we use dynamic programming, where we define a state and transitions that allow us to compute the minimum cost to partition the string step by step. The dynamic programming state is defined as dp, I, j, which represents the minimum cost to partition the first I characters of the string into j substrings. For the base cases, if there are no characters and no partitions, the cost is 0, so dp, 0, 0, equals 0. However, if we try to partition I characters into 0 substrings, that's impossible, so we set dp, I, 0, to infinity. For transitions, we compute dp, I, j, by considering all possible starting indices p for the last substring ending at I. The cost of converting this substring s, p, I, into a palindrome is precomputed, and we use the relation dp, I, j equals min, dp, I, j, dp, p1, j1, plus cost, p, I, to update the state. To efficiently calculate the conversion cost for any substring, we use a two-pointer technique, which allows us to determine the number of changes needed in O, n squared, time for all substrings. Finally, the answer to the problem will be stored in dp, n, k, where n is the length of the string. Dynamic programming is a suitable approach for this problem because it involves overlapping subproblems, such as repeatedly calculating the cost of turning the same substring into a palindrome. By precomputing these costs, we avoid redundant calculations and optimize the process. The two-pointer technique is particularly efficient for precomputing the palindrome conversion costs, as it allows us to evaluate each substring by comparing characters at the two ends and counting the differences. In terms of data structures, we use a dp table dp with dimensions n plus 1 ex, k plus 1, where dp, I, j, stores the minimum cost to partition the first I characters into j substrings. Additionally, a cost matrix cost with dimensions n, x, n is used to store the precomputed cost of converting any substring s, p, I into a palindrome. For the complexity, precomputing the costs takes O, n squared, while the dp transitions require O, n squared asterisk k, iterations, resulting in an overall complexity of O, n squared asterisk k. When implementing the algorithm, it's essential to handle edge cases. For instance, if the string has only one character, no changes are needed regardless of k. If k is greater than the length of the string, it's impossible to partition, and we should account for this. If all characters in the string are identical, the cost will also be minimal since no changes are required. On the other hand, when k equals the length of the string, each character becomes its own substring, leading to a cost of 0. Now, looking at the pseudocode, we first pre-compute the costs for converting substrings into palindromes using the two-pointer technique. This involves iterating over all substrings and counting mismatches between characters at the start and end. Next, we initialize the DP table with appropriate base cases. Finally, we fill the table by iterating through all possible partitions and updating DP, I, J, based on prior states and pre-computed costs. The final step of the algorithm is to return the value stored in DP, n, k, which represents the minimum cost to partition the entire string S of length n into exactly k substrings. Breaking this down, we calculate the cost for each substring to become a palindrome in advance and store it in a 2D matrix for quick lookups. The dynamic programming table is initialized with base cases to handle scenarios like empty substrings or impossible partitions. During the DP transitions, we systematically evaluate all possible partitions and update the minimum cost based on previously computed states. Once the table is fully populated, the result in DP, n, k, gives us the optimal solution. This approach ensures efficiency while addressing all edge cases, making it a robust solution for the problem. Here, we begin implementing the solution by defining a class called solution and a method named Palindrome Partition. The first step in the method is to define a helper function, min_changes_to_palindrome, which calculates the minimum number of changes required to convert a given substring into a palindrome. This is done by comparing characters from both ends of the substring and incrementing a counter, changes, whenever there's a mismatch. The function continues until the pointers meet in the middle, and the total number of changes is returned. Next, we calculate the length of the string S and store it in n. To optimize our solution, we pre-compute the cost of converting every possible substring of S into a palindrome. This is achieved using a 2D list called cost, where cost, I, j, stores the minimum changes required for the substring S, I, j plus 1. We iterate over all possible start and end indices, and for each pair, we use the helper function to determine the cost of making that particular substring a palindrome. This pre-computation allows us to efficiently reference these values later in the dynamic programming solution. After that, we define a 2D list DP where DP, I, j, represents the minimum changes required to divide the first I characters of the string into j palindromic substrings. We initialize DP with infinity to represent uncomputed states and set DP 0, 0 to 0, as no changes are needed to partition an empty string into 0 substrings. Finally, we begin iterating over the string length and the number of partitions to fill in the DP table. To populate the DP table, we use 3 nested loops. The outer loop iterates over the length of the string, I, starting from 1. The middle loop iterates over the number of partitions, j, ranging from 1 to k. The innermost loop, indexed by p, explores all possible previous cut positions. For each combination of I, j, and p, we calculate the minimum changes required to divide the first I characters of the string into j palindromic substrings. This is done by updating DP, I, j, with the minimum of its current value in the sum of DP, p, j1, and cost, p, I1. Here, DP, p, j1 represents the minimum changes to partition the first p characters into j1 palindromes, while cost, p, I1, gives the cost of converting the substring S, p, I, into a palindrome. By iterating through all possible cut points, we ensure that DP, I, j holds the optimal solution. Once the loop's complete, the value of DP, n, k contains the minimum number of changes needed to divide the entire string into exactly k palindromic substrings, and this value is returned as the final result. Here, we start by importing the necessary utilities and defining our solution class. The main method, palindrome partition, takes 2 inputs, the string S and an integer k, which represents the number of palindromic substrings we want to divide the string into. The first thing we do is calculate the length of the string and declare a 2D array, cost. This array will store the minimum number of changes required to convert any substring of S into a palindrome. To populate this array, we use nested loops that iterate over all possible substrings, invoking the helper function min_changes to palindrome to calculate the cost for each substring. Next, we set up another 2D array, dp, where dp, I, j, represents the minimum number of changes needed to divide the first I characters of the string into j palindromic substrings. We initialize this dp array with integer.max_value to indicate that no valid partition has been calculated yet, except for the base case, where dividing 0 characters into 0 substrings requires 0 changes. Finally, we use 3 nested loops to compute the values for dp, I, j, dynamically. For each position I in each possible number of partitions j, we iterate over all possible previous partitions, updating dp, I, j, with the minimum cost based on the pre-computed cost array. Once the nested loops are complete, the algorithm returns the value of dp, n, k, which represents the minimum number of changes required to partition the entire string into k palindromic substrings. To support this process, the helper function min_changes to palindrome is defined. This function calculates the number of character changes needed to make the substring from index start to end a palindrome. It initializes a counter for changes and uses a two-pointer approach, comparing characters at the start and end indices. If the characters are different, the changes counter is increment. The pointers then move toward the center of the substring, and this process continues until they meet. The number of changes is returned as the result. This helper function ensures that we can pre-compute the transformation cost sufficiently, which is crucial for the dynamic programming solution. To solve this problem, we begin by pre-computing the cost table, which tells us the minimum number of changes needed to convert any substring of S into a palindrome. For the given string S equals ABC, we calculate each entry in the cost table. Single character substrings like A, B, and C are already palindromes, so no changes are needed, and their corresponding entries are 0. For the substring AB, one change is required to make it a palindrome, either converting it to AA or BB. Similarly, for the substring BC, one change is needed. Finally, the substring ABC also requires one change, such as turning it into ABA or CBC. The resulting cost table is a matrix where each value represents the number of changes for a specific substring. Next, we initialize the dp table, where dp, I, j, will store the minimum changes needed to partition the first I characters of S into j palindromic substrings. The base case is dp, 0, 0, equals 0, and all other entries are set to infinity, as they represent states we haven't computed yet. With the dp table initialized, we now fill it step by step. For I equals 1, representing the substring A and j equals 1, meaning one partition, the value of dp, 1, 1, is simply dp, 0, 0, plus cost, 0, 0, which equals 0 since no changes are needed for a single character. Moving to I equals 2 for the substring AB, when j equals 1, we calculate dp, 2, 1, as dp, 0, 0, plus cost, 0, 1, which equals 1 because the entire substring AB needs one change to become a palindrome. For j equals 2, where we split AB into two palindromic substrings, the value of dp, 2, 2, is determined by dp, 1, 1, plus cost, 1, 1, which is 0 since no additional changes are required. Finally, for I equals 3, the substring ABC and j equals 1, the value of dp, 3, 1, is dp, 0, 0, plus cost, 0, 2, again resulting in 1 because only one change is needed to transform ABC into a palindrome. For j equals 2, we calculate dp, 3, 2, as the minimum of two options, splitting after the first character or splitting after the second. This gives us a value of 1. The completed dp table now shows the minimum changes for all possible configurations. From the dp table, we find that dp, 3, 2, equals 1, meaning the minimum changes required to split the string ABC into two palindromic substrings is 1. Now, let's look at a more complex example with S equals AB and K equals 3. The first step remains the same, pre-computing the cost table. For this string, the cost table reflects the number of changes needed for substrings like AA, BB, and others. For instance, no changes are required for AA or BB, while 2 changes are needed for AB to make it a palindrome. Once the cost table is complete, we initialize the dp table, again starting with dp, 0, 0, equals 0 and setting all other entries to infinity. Using the same process as before, we then compute the minimum changes for each substring and partition count. This involves iterating through possible splits and finding the option that minimizes the total cost. For s equals app with k equals 3, we calculate values like dp, 5, 3, which represents splitting the entire string into 3 palindromic substrings. For example, we consider partitions like AA, BB, and C and calculate the cost for each split. The result is dp, 5, 3, equals 0, meaning no changes are needed to split app into 3 palindromes. Finally, consider the case where s equals ABCDF and k equals 6. Here, each character must form its own palindrome, and since single characters are already palindromes, no changes are required. Therefore, dp, 6, 6, equals 0. This demonstrates how the algorithm efficiently computes the minimum changes required for different configurations of palindromic partitions, using dynamic programming and pre-computed costs to achieve optimal results. To analyze the time complexity of our solution, we can break it down into 3 main components. First, we have the pre-computation of the palindrome conversion costs, which is stored in the cost array. For each pair of indices, I, j, where I is less than or equal to j, we calculate the cost of converting the substring s, I, j plus 1, into a palindrome. This involves using the min_changes_to_palindrome function, where the time taken depends on the length of the substring. For example, a substring of length 1 takes O1, length 2 takes O2, and so on, up to length n, which takes O(n). Summing these operations across all pairs gives us a total time complexity of O1 plus 2 plus 3 plus n, which simplifies to O(n squared). Therefore, the time required to pre-compute the cost array is O(n squared). Next, we consider the dynamic programming step, which involves filling the dp array. Here, we iterate over I from 1 to n and j from 1 to k. For each combination of I and j, there is an inner loop iterating over p from 0 to I1. Within this inner loop, we calculate the minimum value for the current state using a constant time operation for lookup and addition. The total number of operations can be calculated as follows: the outer loop runs in O(n), the middle loop in O(k), and the inner loop in O(n) in the worst case. Multiplying these together gives a total time complexity of O(n*k*(n), which simplifies to O(n squared *k). Combining this with the pre-computation time, the overall time complexity of the solution becomes O(n squared *k). Now, let's analyze the space complexity. The cost array, which stores the palindrome conversion costs, is a 2D array of size n×n. Since each entry stores the cost for a specific substring, the memory usage for this array is O(n squared). Similarly, the dp array, which is used in the dynamic programming step, is a 2D array of size n plus 1 in fix k plus 1. This means it requires O(n*k) space. Additionally, the helper function min_changes_to_palindrome only uses a constant amount of memory for its local variables, contributing O(1) to the total space. Thus, the overall space complexity is the sum of these components, O(n squared, for the cost array, O(n*k, for the dp array, and O(1) for the constant memory usage. When we combine all the components, the overall space complexity becomes O(n squared plus n times k. This is the total memory required for the solution. Comparing this to a brute force approach highlights the efficiency of our method. A naive solution would involve generating all possible partitions of the string s into k substrings and calculating the cost of converting each substring into a palindrome. Such an approach would require exponential time due to the combinatorial number of partitions, leading to a time complexity of O(2 to the power of n times k. In contrast, our optimized solution reduces the exponential time complexity to polynomial time, specifically O(n squared *k). This significant improvement makes the current solution much faster and more scalable for larger inputs. To further clarify the time complexity, we can analyze the best, average, and worst cases. In the best case, when k equals 1, we only need one partition. Here, the dynamic programming step simplifies to calculating the cost of converting the entire string into a palindrome. The time complexity in this scenario is O(n squared, as it only involves pre-computing the costs. For the average and worst cases, when k greater than 1, the time complexity remains O(n squared *k. This is because the number of operations depends on the size of the dp table and the nested loops, which remain consistent across these cases. Finally, let's validate the mathematical reasoning behind the big O analysis. For pre-computing the costs, the total time is proportional to the sum of the lengths of all substrings, which simplifies to O, n squared. The dynamic programming step involves three nested loops over I, j, and p, resulting in O, n asterisk k asterisk n, or O, n squared asterisk k. Combining these, the total time complexity is O, n squared asterisk k. Regarding space, the cost array uses O, n squared, and the dp array uses O, n asterisk k, making the total space complexity O, n squared plus n times k. These results confirm that the solution is both time efficient and memory optimized for the given problem constraints. When solving this problem, there are a few common mistakes that can trip you up. First, failing to handle edge cases such as very small or very large values of k can lead to issues. If k is greater than the length of the string, it's impossible to partition it into that many parts, and the algorithm may crash or return incorrect results. On the other hand, when k equals 1, the entire string must be transformed into a single palindrome, which requires a distinct approach. Another common error is overcomplicating the process of checking whether a substring is a palindrome. Using inefficient methods, such as manually reversing substrings or repeatedly comparing characters, can lead to unnecessary computational overhead. Instead, optimized techniques like the two-pointer method can simplify this step. Lastly, brute force approaches, where all possible partitions are generated without pruning invalid ones, often result in exponential time complexity, making the solution impractical for longer strings. Efficient pruning and strategic exploration are key to handling such cases effectively. Another area where mistakes frequently occur is neglecting to use memoization or dynamic programming. Recomputing the cost of converting substrings into palindromes multiple times can significantly increase the runtime. By storing intermediate results, you can avoid redundant calculations and improve efficiency. Off by one errors are another common pitfall. These mistakes happen when slicing substrings, especially due to the mix of zero-based indexing and inclusive versus exclusive ranges. Such errors can lead to incorrect calculations of the cost of transforming substrings into palindromes or even invalid partitions. Ensuring careful indexing and double-checking range boundaries can help eliminate these issues. Now, let's discuss some insights that are particularly useful for interviews. A key concept to understand is the trade-off between minimizing the number of cuts and optimizing the cost of transformations for each substring. This trade-off is a hallmark of dynamic programming problems. Recognizing that problems like this often involve substrings and transformations is crucial. A common optimization strategy is to pre-compute results for all possible substrings. For instance, pre-computing whether a substring is a palindrome allows you to avoid redundant calculations later. Additionally, interviewers often focus on your ability to reduce redundant computations using memoization or tabulation, so it's important to articulate how overlapping subproblems are handled efficiently. Finally, when discussing edge cases, always clarify scenarios like k len s or k equals len s to ensure your solution aligns with the problem's constraints. If you're looking to deepen your understanding or prepare for related problems, there are several LeetCode questions worth exploring. Palindrome partitioning, problem 131, involves partitioning a string such that each substring is a palindrome. Palindrome partitioning 2, problem 132, takes this further by asking for the minimum number of cuts needed to achieve such partitions. Longest palindromic substring, problem 5, focuses on identifying the longest palindrome within a string. Finally, problem 1593, split a string into the max number of unique substrings, challenges you to maximize the count of distinct substrings in a partition. These problems share overlapping techniques and concepts, making them excellent practice for honing your skills. Lastly, let's consider some alternative approaches to solving this problem. Dynamic programming, when optimized, can be incredibly powerful. While it requires a higher upfront complexity, such as pre-computing palindromic substrings, the payoff is significant for larger inputs. It's the go-to approach for competitive programming scenarios. Another option is greedy approximation. While faster to implement, it doesn't always guarantee optimal results, so it's better suited for situations where exact solutions are infeasible, such as extremely large inputs. Backtracking with pruning offers a more conceptual approach, which can be easier to implement. However, its efficiency heavily depends on having strong pruning logic. This method works best for small to medium input sizes, where the solution space is manageable. Choosing the right approach depends on the constraints and requirements of the problem you're solving. Great job making it to the end. Today, we tackled Palindrome Partitioning 3 using dynamic programming. We discussed the importance of optimizing time and space complexity and highlighted key takeaways for solving similar problems. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!